We're going to find a polynomial p of x of degree 4 with zeros -3, -I, and -2 with a multiplicity of 3. So p of x takes the form a, which is a constant. We don't know what it is right now, times x minus c1, times x minus c2, times x minus c3. Let's change this to a multiplicity of 2, times x minus c4. So -3 is our c1. And we have minus and negative, which turns to a positive. X minus I times x minus 2 times x minus negative 2. So these all change to a positive. And we need to FOIL. So we're going to FOIL the first two binomials together. X squared plus ix plus 3x plus 3I. FOIL the second two together. X plus 4x plus 4. And now we need to multiply all of this out, which is a lot of work. So we're just going to leave it like this. When you multiply this out, p of x goes to a times x to the fourth plus 7x cubed plus ix cubed plus 16x squared plus 7ix squared plus 16ix plus 12x plus 12I. Now, there is no a just goes to 1 because there's nothing left, so we don't actually need to write it. We're going to find all four zeros of p of x equals 3x to the fourth minus 2x cubed minus x squared minus 12x minus 4. So our a sub 0 over a sub n, 4 over 3. So possible zeros, positive negative 1, positive negative 2, positive negative 4, positive negative 1/3, positive negative 2/3, positive negative 4/3. So like I said, use a graphing calculator, plug it all in, see what works out. It's going to come out that 2 works, so we're going to use synthetic. So we now have p of x equals x minus 2 from our factor times 3x cubed plus 4x squared plus 7x plus 2. So we're going to have possible zeros, positive negative 1, positive negative 2, positive negative 1/3, and positive negative 2/3. plug it in again, we're going to find that 1, positive, negative, and 2, positive or negative, do not work, but negative 1/3 works. So set up synthetic. Luckily, this one's working out well with multiplying by a fraction. So now we are at x minus 2 times x plus 1/3 times 3x squared plus 3x plus 6. And I'm going to go ahead and factor out a 3 from the trinomial. I'm going to put it up front. And we know that we had to use the quadratic formula here to solve for x. So this one gives us 2 answers. -1 plus or minus root -7/2, which goes to -1 plus or minus I root 7/2. We also get -1/3 and 2. Conjugates of zero theorem. If the polynomial p has real coefficients, and if the complex number z is a 0 at p, then its complex conjugate, which you have z with a line over it, is also a 0 at p. So, putting this into a problem, find a polynomial p of x of degree 3 that has integer coefficients and zeros 1/2 and 3 minus I. So, we get p of x, and we have 3 zeros. One of them is going to be x. Let's make that a 2, not 1/2. X minus 2, x minus 3 minus I, and its conjugate, which is 3 plus I. Okay, so we're going to work with x minus 3 minus I. And x minus 3 plus I, so that goes x minus 3 plus I times x minus 3 minus I. So we're going to multiply this out. Get x squared minus 3x minus xi minus 3x minus plus 9 plus 3i. And then we're going to get an xi, line it up, minus 3i, and then minus I squared. So we get x squared minus 6x. These cancel. Well, let's hold off on the plus 9. 3i minus 3i cancels. Negative I squared becomes negative 1, which goes to a positive. Add it with the 9, get positive 10. Now we're going to bring down our linear factor, x minus 2. Multiply this out. We get x cubed minus 6x squared plus 10x minus 2x squared plus 12x minus 20. So if we combine over all of our terms, we get p of x equals x cubed minus 8x squared plus 22x minus 20. And this is our answer. Okay, a quadratic polynomial with no real zeros is called an irreducible over the real numbers. It cannot be factored without using complex numbers. So we have the linear and quadratic factors theorem. Every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. So factoring a polynomial into linear and quadratic factors, we have p of x equals x to the fourth plus 2x squared minus 8. So we see an x to the fourth and an x squared, negative 8 and 2. So this is factorable to x squared plus 4 times x squared minus 2. And we can factor the x squared minus 2 into x plus root 2 times x minus root 2. And to get it completely factored, we need to do the same thing with x squared plus 4, but it will have imaginary numbers. X, let's change colors. X plus 2i times x minus 2i. The way I'm getting these numbers is if I took x squared plus 4 equal to 0 and solve for x, I would get x to be positive and negative 2i. Just like if I took x squared minus 2 equal to 0, I get x squared equals 2, and I would get x equal plus or minus root 2. And then I'm just plugging in these numbers into the linear factors. Oops, that one actually goes further.